Welcome back to our next problem solving and equilibrium lesson. In this lesson, we are going to be looking at a problem solving technique called an icebox. So in the last lesson, we looked at reaction quotients, the Q, and comparing it to K in order to determine if a system's equilibrium or not. By the end of this lesson, you will be able to use an icebox to calculate species that are not at equilibrium and convert them into equilibrium concentrations. So this method of problem solving is going to be useful in all aspects of equilibrium calculations. It's extremely useful. It's pretty much universally known in chemistry courses as an effective problem solving technique. You will be using this problem solving skill if you're given initial concentrations and you need to change them to equilibrium concentrations. That's where you get this handy dandy acronym. On nearly every single AP exam, the first free response question, which is always a long, like 20 to 25 minute problem, is an ICE calculation. It's an equilibrium problem that involves an ICE calculation. So you're going to be doing a ton of these over the next couple of months. So here's an example of how this would be set up. You could be given a balanced equation, and you may or may not be given the K values. If you're not given the K value, you'd have to solve for it. But if you are giving a K value, you're going to be using that when you set up your equilibrium expression. So what you do is you would write what the K expression would be, which in this case for this equation, it would be the concentration of B over the concentration of A. So very simple. Your next step is to make an ICE table. Do me a favor, when you're doing these problems, solve them this way. If you look at the scoring keys for AP exams, they look for this. It makes your problem solving very methodical. It makes it neat and organized. So throw me a bone here, okay? So you set up this ICE table, and I stands for initial concentration, C stands for the change, which is a stoichiometric relationship from the equation, and E is going to be the concentrations at equilibrium. So we are going to start out by writing our initial concentration of A, which is 0.850. We do not have an initial concentration of B because it's 0. Now the change is going to be, obviously in this case, the concentration of A is going to drop and the concentration of B is going to rise. And the change in A is going to be a negative change, and the change of B is going to be a positive change. We don't know the quantity it's changing by, but we do know based on the coefficients how the changes will be in relation to one another. So we're going to say for A is it's going to lose X quantity of concentration. And since A and B's coefficients are the same in the equation, B is going to gain an X quantity. So now this equilibrium concentration value for A is going to be 0.850 minus X, and the concentration at equilibrium for B is just going to be X, 0 plus X. Now what we're going to do is solve. We're going to plug the equilibrium line from our ICE table into our equilibrium concentration and solve for X. So we have the K value of 24. We have the concentration of B at equilibrium, which is X, and we have the concentration of A at equilibrium, which is 0.850 minus X. So we're going to cross multiply. So be careful with your algebra here. Don't make silly math errors. So 24 times 0.850 is 20.4, and that's going to be minus 24x, and then that's equal to x. So we'll add 24x to both sides, so we get 25x on the right, and that's equal to 20.4 on the left. Then we will divide by 25 on both sides, and we are left with 0.816 for the value of x. Now we can calculate what the final concentration of A would be at equilibrium and the final concentration, the equilibrium concentration of B. So we just substitute x into this E line. So the concentration of B is at equilibrium is obviously just going to be 0.816 molar. The concentration of A at equilibrium is going to be 0.85 minus 0.816, and that is equal to 0.034 molar. So these would be the answer to the question, the concentrations of A and B when it reaches equilibrium. Now, for this problem, we can do the does this make sense test because we're given this K value. Remember from the earlier lesson, if K is greater than 1, that means that at equilibrium, the quantity of products is going to be greater than the quantity of reactants. And that makes sense. B is our product, and B is a higher number than A, our reactant. Our numerator was higher than our denominator. So that's a very straightforward example of how to solve an ice problem. But wait, there's more. So here we have a system at equilibrium. We have our iron and thiocyanide ions, and we have our initial concentrations of 6 molar and 10 molar. And then it tells us the equilibrium concentration is 4 molar for the product ion. And now it's asking us to figure out the value of K for this reaction. So we can write the K expression and now we can solve and fill in the rest of our ice table. So we started with no product, and we ended at equilibrium with 4 molar concentration of product. So the change values, we have no choice but to lose the iron, and the thiocyanide ion is going to be lost at the same proportional amount because the coefficients are the same. And then the product is going to gain by the same stoichiometric amount because its coefficient is also 1. So right now, we know what x is equal to, which makes our job a lot easier. So because 0 plus x equals the 4 molar, therefore x is equal to 4. So we can substitute x in here, we can substitute 4 into each of these to figure out the equilibrium concentrations of each of our reactants. Now we can plug those values in, product divided by the reactants, they're each raised to the first power, so that's easy, so 4 over 12, so the K value is 0.33. So you could be given equilibrium concentration for something and work backwards from that. And again, all you're looking at here is how they're changing based on the coefficients in the balanced equation. So what we can do here now is look at another version of this problem where we already have K from the previous example. And we can use K to figure out the equilibrium concentration of the product. So we have an initial 10 and 8. We don't have any of that product. So we're looking at our quantities here. And we can substitute into our equilibrium expression. So K is equal to product over our reactants, so 0.33 because we solved that from before, and that's a constant, over equals x over 10 minus x and 8 minus x. Now, if you see what we're doing here, we're going to have to combine this. I think it's called a binomial. I can't remember, but math it. To simplify here. So 0.33 equals x over 80 minus 18x plus x squared. So when you end up simplifying this as much as possible, you're going to see that you're going to need a quadratic equation to solve this problem. This is a possibility, in real life chemistry. You have a solver function in your graphing calculators, but in the AP world, the AP exams, you won't have to use quadratic formulas to solve these equations. I will show you an example where you're going to be dealing with perfect squares, or you might be dealing with scenarios in which this minus x factor ends up being negligible in the grand scheme of the problem. And I will show you examples of where that would be the case, and it helps to simplify your math. So I wanted to show you this one just to give you an example of something where you might encounter something where you'd have to use the quadratic equation. But I'm not going to bog you down with that kind of math because in the scheme of the exam, it's not going to be testable. So let's look at another simple example here where we do end up with squares, but it ends up being simplifiable, if you will. Okay, so for this problem, we have a mixture of 0.5 moles of hydrogen, 0.5 moles of iodine placed in a 1-liter flask. So if we have moles and liters, we have the concentrations of 0.5, initial concentrations of 0.5 and 0.5 molar. We have no hydrogen iodide initially. It gives us the Kc value, and it's asking us to calculate the concentrations of all of our species at equilibrium. So since we only have reactants in our system initially, those reactant concentrations are going to be dropping over time. Now the product is going to be rising, but we have to take into account the coefficient here. Because the coefficient of the hydrogen iodide is different than the hydrogen and the iodine, it has to go in there. So the equilibrium concentration of the hydrogen iodide is 2x, and each of the reactant species would be 0.5 minus x. So now what we can do is we can write our equilibrium expression. So we have products, and we're going to square that, over reactants. So now we're going to substitute our values in. We have 54.3 for the equilibrium constant. We have 2x quantity squared. Be very careful with that. It's 2x quantity squared over 0.5 minus x times the quantity 0.5 minus x. So right there, we can rewrite that as 0.5 minus x quantity squared. Okay, so this is a scenario that you could encounter on an AP question, but you can then simplify this. You can take the square roots of both sides to eliminate this from your problem solving. So we can do that. That will end up with 7.37 equals 2x divided by 0.5 minus x. So now we just have an algebraic equation to solve. So we will cross multiply. So 7.37 times 0.5 is approximately 3.68, and that's going to be minus 7.37x. That's equal to 2x. So now we can add 7.37x to both sides. Divide by 9.37 on both sides, and you end up with 0.393 for x. So we're not done. That's just the value of x. We need to now substitute x into our equilibrium concentration line to solve for those equilibrium concentrations. So the hydrogen and the iodine equilibrium concentrations are going to be the same because that line is the same. So the concentration of the hydrogen is going to be equal to the concentration of the iodine, and it's going to be 0.5 minus 0.393. And that is equal to 0.107 molar for both of them. And then the concentration of the hydrogen iodide is equal to 2x, which is 2 times 0.393, and that's equal to 0.786 molar. So again, we can do the does this make sense test. We're given a K value larger than 1, which indicates that at equilibrium, there's a greater quantity of products present than reactants, and that is the case for this problem. This next example is using the same equation. So we'll have the same K value. K is going to be equal to 54.3. But now instead of starting out with no product, we are starting out with some product. So in this example, when you're given an initial quantity of every substance and it's not 0 for any of them, you need to calculate Q first to determine which way the reaction is going to proceed in order to reach equilibrium. So you're going to have to calculate Q, compare it to K to determine am I going to have a loss of reactants and a gain of product, or am I going to have a loss of product and a gain of reactant? So you need to do that. That is a huge concept that students often overlook on AP questions. So we're going to calculate Q for this one. So Q, because we don't know if this is at equilibrium or not, it's a product, 0.04 squared over 0.5 times 0.5, and that is equal to 0.0064. So if Q is equal to 0.0064, Q in this case is less than K, so our reaction is going to proceed in the forward direction more rapidly in order for the system to reach equilibrium. So since it's proceeding in the forward direction, now we know that our reactants are going to be decreasing in quantity and our product is going to be increasing in quantity, just like it was in the last one. .04 plus 2x. Okay, so now we can figure out x by using the equilibrium expression. So we have 54.3 equals the quantity 0.04 plus 2x squared, because of the equilibrium expression, divided by the quantity of 0.5 minus x, and that's going to be squared because I'm doing that twice. So again, I can take the square root of both sides to knock out those exponents. So solving for that, 7.37 equals 0.04 plus 2x divided by 0.5 minus x. So now we'll cross multiply. 3.68 minus 7.37x equals 0.04 plus 2x. I'll add the 7.37x and I'll take away the 0.04 from both sides. So this would be 3.64, and that would be equal to 9.37x. Divide by 9.37 on both sides, and I end up with 0.388 for the value of x. Now I can substitute that into the equilibrium. Yeah, I know these are long problems, just deal with it. I can substitute x into the equilibrium line, so we can solve for the equilibrium concentration of hydrogen, which would be equal to the equilibrium concentration of iodine, because we started at the same place, we lost it at the same rate. So that is equal to 0.5 minus 0.388, which is 0.112 molar for each of those. And then for the hydrogen iodide, it's 0.04. I didn't do that one. 0.04 plus 2 times 0.388. So that is, I solved all these other ones, I just skipped that line. That's equal to 0.816 molar. So again, this makes sense that since our K value is so large, our final concentration of product should be greater than our concentrations of reactants when it reaches equilibrium. So that's really the last example I wanted to give you for this. When you are solving these problems, and we're going to do a bunch of these in class, if you look for small K values, so if K is less, pretty much 10 to the negative fifth is your cutoff. That if the value is that small, when you end up doing the math, the x value might be negligible in your problem, which really will simplify things for you and prevent you from having to do quadratic equations. It really comes up more when we talk about acids and weak bases, but you might see a couple in this unit, and I'll always reinforce that in class when we go over it. If x is large enough to impact equilibrium values, you must subtract it from the initial concentration. Your math will be simplified if the problem's a perfect square, just like we were doing before. So if it's not, you have to use quadratic, and you're allowed to use your calculator with a solver or program for solving quadratic. So if you have a quadratic formula, a program in your calculator already, you will not be asked to erase the memory of your calculator prior to the exam. So if you want to use it and you're comfortable using it, you can. But I'm telling you that on the AP exam itself, you won't be asked to solve problems that require the use of the quadratic equation. And this last point, this is very important and often forgotten by students. If none of the initial concentrations are zero, meaning I have non-zero numbers in all of those I spots, then you must calculate Q before you fill in the rest of your ICE table, compare it to the given K value, and determine which direction your reaction's actually going to proceed in. So after this lesson's completed, you should be able to calculate concentrations using an ICE table and substitute your values into equilibrium expression. From the prior lesson, you should be able to use reaction quotients to determine if the system's at equilibrium, and then use an ICE table appropriately. We will do a ton of practice in class, but I want you to have an overview of what this means so we can just hit the ground running.